Out in the farthest reaches of our solar system, Neptune sits in complete silence. It appears as a perfectly still, frozen sphere of blue. On Earth, weather operates on a predictable loop where liquid water evaporates, condenses into clouds, and falls back to the ground. Up here, that concept of meteorology is completely useless. Deep inside this gas giant, the precipitation isn't made of water droplets. The weather system here manufactures massive, solid diamonds. To observe how a ball of freezing gas creates precious stones, we have to abandon the surface entirely and plunge thousands of miles downward toward the planet's core. The tranquil blue shell hides the most extreme storm system in the solar system. As we plunge past the upper cloud layer, the sunlight completely vanishes. The clear blue atmosphere thickens into a dark, violently swirling chemical soup. The dominant compound in this soup is methane. Methane is a molecule made of one central carbon atom bound to 4 hydrogen atoms. It gives Neptune its blue color, and it holds the raw carbon required to build precious stones. Our chart tracks the physical extremes of this dive. Atmospheric pressure spikes exponentially with depth, becoming millions of times greater than Earth's sea level. A second line shows temperature rising alongside pressure, hitting thousands of degrees. We are suspended in immense heat and suffocating weight. At these specific depths, the standard rules of physics and chemistry can no longer hold the atmosphere together. At this threshold, methane molecules fail. The bonds holding carbon to its 4 hydrogen partners violently snap. Lighter hydrogen floats upward. Trapped by extreme pressure, the isolated carbon atoms bond together, snapping into a rigid crystal lattice, a 3-dimensional atomic arrangement creating a solid diamond. Heavy, solid gemstones are now suspended inside a soupy, superheated liquid mantle. Because these new diamonds are vastly denser than the surrounding fluid, gravity takes hold. They begin to sink. This continuous process creates a relentless, heavy downpour of solid diamonds falling toward the planet's core. The diamonds plummet thousands of miles further inward, eventually accumulating in a dense, massive layer wrapped tightly around Neptune's solid rocky core. For decades, astronomers struggled with a specific measurement. Neptune radiates over 2.5 times more heat into space than it receives from the distant sun. This diagram shows the heat waves radiating outward from the planet's interior. The immense friction generated by millions of dense diamonds physically scraping through the viscous mantle produces massive amounts of thermal energy, perfectly answering why the planet is so hot. If we travel back out for the blue clouds and look at the sprawling galaxy, the data points to a broader conclusion. This bar chart compares the known frequency of different exoplanet types across the galaxy. Exoplanets are planets that orbit stars outside our own solar system. As you can see, the tallest column belongs to ice giants, planets composed largely of elements heavier than hydrogen and helium, just like Neptune. Since ice giants make up the largest planetary demographic in the known universe, these massive, relentless storms of falling diamonds are likely the single most common weather pattern in the entire cosmos.